up, everybody? Welcome to another episode of Let's Ask Paul, the podcast where we answer your pressing electrical questions. Again, my name is Paul Abernathy, and welcome to Let's Ask Paul. If you've got questions, you can submit them as well over at paulabernathy.com. I do my best to answer those questions either in an email, or if I find them very beneficial to other listeners, I will turn it into a podcast, much like the one that I'm doing on today's episode. So, look, all of our programs are sponsored by Electrical Code Academy Incorporated over at electricalcodeacademy.com or masterthenec.com, .net or .org, it doesn't matter. And we teach electrical code. And we typically don't just teach electrical exam preparation. So that's kind of what we're known for. And that's one of our programs, our Fast Tracks Black program. But we teach all aspects of the National Electrical Code. We consult on many things. We give advice, and you can agree to disagree with a lot of our interpretations. That's totally up to you. That's the beautiful thing about it, is that everybody's entitled to their opinion, and we give ours freely. In fact, I don't shy away from it. I make it very aware out in the public domain of my different positions, which, again, you can disagree with. It's perfectly fine. Doesn't make you any better or any less. It's just your opinion, and you get to run with it. But on today's episode, we're going to be talking about a transformer application where somebody's interested in how to do a step-down transformer, and they've got a bunch of variables. But I'll tell you up front, a lot of variables are missing. We don't know whether this is a delta to delta, a delta to Y. We have no idea. All we have is some voltages, and I can get these voltages out of this installation, whether it's a delta or a Y. So, again, it could be a delta high leg, it could be a delta to delta with a delta high leg getting the voltages they need. And I don't know those variables, so we're going to do our best to try to answer it at a very high level, and hopefully we give some guidance to this. I have already responded to this one via email, but I think it would be a good episode to elaborate on. So that's why I'm bringing it up. Now, a couple of things that I'll tell you as we get into this. I do my best to try to break down the different elements of it. So sometimes it can rattle on a little bit. And again, I apologize. You can pause, you can fast forward, you can do whatever you like in these episodes. But I try to give additional commentary when necessary for the person that submitted the question. Because again, this is all about the person that submitted the question. And I want to have an effort to answer their questions and give them any additional insight that I might be able to give them. So I want to make sure I stay focused on that. All right, here's the question. It says, "Hi, Paul. I want to let you know that I check in on your online channel frequently, and you are setting the bar for electrical education. If you can help me with this question, I will pay you for your consulting time, or I will purchase one of your courses." Okay, so that's kind of the beautiful thing about Let's Ask Paul, right? Is that I do my best to answer questions for you, and you don't have to pay anything. Now, this gentleman gave a donation, which you can do on our Let's Ask Paul portal at paulabernathy.com if you want to say thank you for me helping you out, or if you've listened to other of our Let's Ask Pauls. I don't know what episode we're on now, but it's in the 60s. And of course, I have literally hundreds of other videos and podcasts that you get to see if you're in our monthly exclusive program over on our website. So if you want to see calculation videos, you want to get rebroadcasts of our Wednesday nights, you want to see some of my past done webinars, like the grounding and bonding or the swimming pool ones, that's extensive. Check that out. It's $9.99 a month, or you can do $119 annually. And it's just a great deal for what you get. And you also get all the new stuff that'll be coming out. I'm sure I've told many of you on social media that we've just purchased some expanded equipment, some more cameras, some other types of equipment. We just got a brand new Rodecaster Pro 2, which replaces our Pro 1, or the original Gangsta Rodecaster Pro. And so we're constantly putting it back into our courses and our programs to bring you content. We're not about getting 500,000 followers on social media. Because again, they typically are not the people that we're looking for. That's the people that are like looking at videos and like listening to podcasts about the work they do. I don't do that thing. I do code. I don't want to post videos of me installing NMB or bending conduit. It's not my thing, right? I'm teaching you the code. And I believe everybody needs to be well-rounded and learn all aspects of the code. Now, on today's episode, though, I'm going to be giving my opinions to this installation, and based on what I think is necessary. Now, before I get started into this, let me read it all a little bit more here. And then I'm going to give you something to think about to the person that submitted this that you might be able to get away with. And it might be cheaper for you. So let me go on and finish this question now. It says, if you can help me with this question, I will pay you for your consulting time or I will purchase one of your courses. We are a 3-man company who do about 90% residential and about 10% commercial work. We do very good work, but there is a restaurant that has asked our company to install a piece of equipment, and I'm not 100% sure of my ability to fully understand Chapter 450. Well, I think you mean Article 450. It sounds like you want a transformer, and it sounds like you're trying to step the voltage from 480 to 208. A couple thoughts on that before I finish your question part here. If it's 480 volt in the restaurant, I'm sure they have lighting that is not going to be 480. I'm sure there's another voltage in there. Whether this is 480, 277, I have a hard time believing they don't have any 120 volt loads in there. So I'm not sure what this total system is. But when you have 480, it makes me think you have something else in there. And again, it's very common to try to get 480 in a building and then need to get down to 208 volts because it might be 480, 277. And then there might be a 480 and it steps it down into a 120, 240 to be used for your single phase loads and all. I get it. But I'm not 100% sure what you're going because you didn't tell me whether it was delta to delta. We're looking for a delta high leg transformer. Are we delta to Y? So I am not trying to make sure that I tell you something that's not germane to what you're asking, but is lacking a little bit of the information. So I'm doing my best. Now, when it comes to the building, the restaurant, there is a possibility now that since you have this voltage class there, let's say it was to the building as a service, you have the 480 coming to the building, for say 480, 277, let's just say, then you might be able to get another service to the building that ultimately may be cheaper than buying a transformer and doing all the associated wiring, all for just one piece of equipment. Again, it may be something that you could put in another panel, another service drop, the utility will bring it over to it. It's only supplying one load, but again, if they got this one piece of equipment, it might expand their horizon to other pieces of equipment. I'm just saying it might be an option under 230.2. You might be able to bring an additional service to this building, and maybe under 230.2D, which is different characteristics. Okay, so this is different voltages. So you might have a 480, 277 there, but you might be able to bring a 120, 208 there or something like that, and you'd be okay. You'd be okay to do that. Maybe that's more cost effective for you. But if not, you're going to go with the transformer route. So I'm going to kind of stick with your question, but I wanted to make sure I threw that out there in case that was a condition, because yes, you can have more than one service to a building if you follow all the rules in 230.2. And you have some special conditions, special occupancies, capacity requirements, different characteristics. If any of that's in play, then you can have more than one service for a building. So just kind of keep that in mind, put that in your back pocket in case you ever run into that situation. All right, let me go on here. Since we're going to stay in the transformer mode, it says, I know you are a busy person. If you are so inclined, here is the scope of the work. Okay, let me read this out totally here. It says, I have a 480 volt panel and I need to power a 208 volt HVAC unit. The full load of the unit is 78 amps. Okay, so we're going to go with that being the load. That is the load. We'll assume this is all a nameplate. And it has a maximum overcurrent protected device of 100 amperes. So this tells me the HVAC equipment has a nameplate, says minimum circuit ampacities, 78 amps. The maximum overcurrent protection is 100 amps. So no different than your normal HVAC application. Gotcha. The only thing we're doing is installing a transformer to make sure it can handle this load. That's it. Don't overcomplicate it. That's all we're doing for it. If that's what this person is doing. Sounds like that's what they're doing. It says the HVAC unit is located outside, and I plan on running the 480 volt power on top of the roof, approximately 330 feet. Wow, that's a serious restaurant. I'm just saying. Installing a primary disconnect at the end of the line near the transformer, primary side, installing a transformer, and then taking the 208 volt power to a disconnect on the HVAC unit, and everything will be outside. So I plan on making sure the electrical gear is rated for outdoor condition. Okay. So this makes sense. What you're doing here is you're saying, okay, I'm going to go from a 480 volt panel. This is your choice. And I'm going to go from a breaker, and I'm going to go out in a raceway. I'm going to go across the roof, an excessively long distance, and I'm going to hit a disconnect for the transformer. And then I'm going to go feed that transformer, and then I'm going to come out on the secondary side, and I'm going to feed a disconnect for the HVAC unit. Okay? Sounds about what's happening, what's taking place. Now, a couple observations first. The disconnect that's required for the transformer that you're putting at the actual transformer, you may be able to get away first. Now, I'm not trying to tell you what to do. I'm just telling you how you might save a little money depending on the condition you might be dealing with. So if you're dealing with that transformer, you may be able to use the breaker that's back in the actual 480 volt panel as your disconnecting means, as well as it's going to be the overcurrent protection for the primary side of the transformer. But it might be able to serve double duty as the disconnect, because you can go over and look at 450.14. Now that's disconnecting means, and that's specifically for the transformer. It says, transformers other than class 2 or class 3 transformers shall have a disconnecting means located either in sight of the transformer, which is, what you want to do. You want to put one right beside it, or in a remote location. Well, I'm saying this remote location could be back at your 480 volt panel. It says, we're located in a remote location, and that is remote from where the transformer is at. It says the disconnecting means shall be lockable open in accordance with 110.25, and its location shall be field marked on the transformer. So on this transformer, you put a phenolic panel, a label. Well, obviously, it's got to withstand the conditions of use. Can't be just like an inkjet. You get the picture. And it will tell you where your disconnecting means is. And if the disconnecting means is not right beside it like you intend to do, but you instead want to put the one back, use the breaker that's back in the 480 volt panel, then you can do that as long as that breaker can meet the lockable open and all the rules that are in 110.25. If and you can do that, and if and is a word I just made up. If and you can do that, then you will not need the disconnecting means right there next to the transformer on the primary side. Okay? So that breaker that's back in the 480 volt panel can serve as the overcurrent protection for the transformer, but it also can serve as the disconnecting means provided you do the labeling back at the transformer. You get me? Okay. So that might save you a little money in how you want to run your installation. Okay. The only other comment I'll make is the 330 feet. Just don't forget about voltage drop. I know it's not in the code, but it's a prudent design. You want to make sure this equipment runs efficiently, and you don't want to be called back because stuff gets burning up because of excessive length and stuff. So you might be ended up, putting larger conductors in anyway than what's going to be based on our calculation today. But I just want you to kind of keep all that stuff rattling around in your brain as you do that. Okay. Now, some of your questions you're going to have here, I'm going to read them. But now, when you're at your transformer, now you're going to the secondary, to the HVAC disconnect that you're going to put in. And a 440 is going to require you to have this disconnecting means. And it's going to be there for the HVAC unit. Okay. Now, ultimately, you're also going to need overcurrent protection as well. Okay. So that's going to all be incorporated in your disconnecting means that is right there off of the secondary conductors of the transformer. So you're going to be doing it all in there. So that's where you're going to need a disconnect for that. Okay, so we just kind of get that. That's one of your questions, but I just want to, let's get that out of the way up front. Now, you say that this HVAC unit has a load is 78 amps, and you say it has a label tells us it's the maximum overcurrent is 100. Okay, and we're going to try to keep this simple. So when I'm sizing this transformer, so that's the next step. When I'm sizing this transformer, I have to make sure that at the load, which is on the secondary side, that I have to make sure that this transformer can handle 78 amps. Well, a 30 kVA transformer can handle 83 amps. Now, where do we get that? Now, again, we're assuming all of this is three-phase, and this is 208 volts, three-phase. So you take the 3208 times 1.732, that gives us 360. And that's what we're going to use in our math. So if it's a 30,000 VA transformer or 30 kVA, we just converted that into the VA. And I'm going to divide that by 360. That's 83 amps. So that a 30 kVA transformer can handle 83 amps. Now, there's many people out there to design these on a regular basis, and I'm not talking code here, but we'll say, look, that is right at the cusp of what that transformer can handle, and they would like you to increase that. They would like you to say, look, I would say go to the same size as your maximum overcurrent protection of 100 amps, and then size your transformer to that. I'm saying that you can size it based on your load, and your load is 78 amps. But there are prudent designs, and sometimes they make sense to say, I'm going to go a little larger. Now, the problem with that is it could throw you into a transformer that is more costly. For example, we're starting out here as a minimum of a 30 kVA, but I believe to handle 100 amps, you probably will going to have to jump up to a 45 kVA because in three-phase transformers, they kind of jump in size, right? Once you get to 30, it goes like 15 kVA, 30 kVA, then it jumps to 45 kVA for those 480 208 volt transformers, three-phase. So again, it kind of jumps a little bit, whereas a 480, 277 single-phase transformers have a bunch of different ratings, right? That gives you a little more like a 5, a 7.5, a 10, a 15, a 25, a 37.5. You know what I'm saying? So in a three-phase one, 480 volt to a 12208, let's say Y, and you haven't told me what you're dealing with here, so I'm just kind of leaping a bit. It jumps from 30 to 45. So a 30 kVA is going to handle your 78 amps okay. A 45 kVA would handle more amps. And if you do the same type of math, a 45,000 divided by 360 is going to be 125 amps, which many people that design these systems say that gives you a little bit of an extra cushion on this transformer. Okay. Remember, the load is still 78 amps. And that nameplate has already been derived from the values that are in 440. So it's already done. We're just choosing the nameplate. Remember, no different than what you would do if you were sizing this for service or something like that. No different. Okay? So again, knowing what our loads are, that's how we're sizing everything. Okay? And we need to know what that transformer can handle. And it's assuming that you've already done all this and you're telling me that at the end of the day, it's 78 amps because that's all you've given me. I don't know anything else than that. So we're just gonna go with the 78 amps. So a lot of times the 45 kVA might be the best option. It does give you a little bit more capacity. You are going to, for example, you are going to need to have a service receptacle for this HVAC and within 25 feet. So depending on what you're supplying on this secondary, maybe it's a 12208 volt panel. And maybe at that point you need to put a panel instead of the disconnect just for the HVAC. Maybe you need to install a panel and then you'd be able to get load out of that to be able to supply a 120 volt receptacle that's for servicing of this HVAC equipment because you still have those rules you still got to meet. So, I mean, you've got a bunch of different options to think about. And by going to the 45 kVA, you get some more capacity out of it. All right. But if we're just talking the HVAC unit and that's it, then okay. But remember, you still have other rules you have to meet. And again, the way it sounded, you didn't have any 120 volt loads in this building. I can't believe you wouldn't. So maybe there is a receptacle already within 25 feet of the HVAC. But I'm just giving you things that you have to think about when you're doing this. Okay. Because if I let you put an HVAC system in and you wire it, then I'm going to expect that receptacle for servicing. Okay. All right. Just stuff to think about. Okay. So whatever I choose, 30 or 45, totally up to you at that point. Minimum 30, comfort level 45. Everybody's different. This isn't exam prep. This is real world. Okay, so the next thing that we're going to look at is, okay, we've sized our transformer Now we're going to talk about what? Let's just say we went with the 30, and we'll even look at the 45, but we'll just start with the 30. We went with the 30. Okay? All right, so with this 30, one of the things that we're going to do is say, okay, what is the overcurrent protection for the primary side? What is that? What's the maximum that can be? All right? Now, you could do this based on the load, but we're going to be doing this based on our transformer. Is how I'm going to be doing it for you. Okay, so we found out what the load. So let's get some currents involved here. Let's get some values here. And again, based only on what I know, if we did a 30,000 VA volt amperes or 30 kVA transformer, the primary current, maximum primary current, since it is 480 volts on the primary side. Then we take that as three phase. So we do the 480 times 1.732. And that'd be, let's go on and get the exacts here. So 480 times 1.732 is 831.36. Now, in the real world, you could probably get away with dropping the 0.36. Okay, and just working with 831. Okay, it would be fine. So we're going to do that. We're just going to work with the 831. This is an exam prep. It's not all I do is exam prep, folks. Okay. So 831. So now let's do our math and find out what our current is for the primary side or the capability of this for this 30 kVA transformer. So I'm going to take the 30,000. Remember, the kVA doesn't change whether you're working primary or secondary. 30,000, I'm going to divide that by 831, and that is 36.10. So I'm just going to drop that 0.10. So I've got 36 amps of potential capacity for this transformer on the primary side, okay? All right, so that is, so one of the things that I look at now is like, okay, now that I have this 36 amps, then I can go to 450.3B because now I want to protect this transformer. And so it's going to allow me to do something. All right, and I'm going to start off by simply saying primary only protection, okay? I'm going to ultimately have protection on the secondary, and I've got rules for the secondary. But we're going to start out with and talking about the primary and just following those rules, okay? So if I don't exceed 125% on the primary, then I don't require any secondary protection for this transformer. So that's typically why we follow that. All right, so let's kind of do this and work our way out. I'm just giving you my thoughts here on how I would do this for your question. All right, so you got your code book. Go to 450.3b, and we're going to do primary only protection. If that's the case, then we don't exceed, and we're obviously going to be currents of 9 amperes or more, obviously, because we have 36 amps. So we're going to go to 125%. So I'm going to take this 36 times 1.25, and that is 45 amps. Okay, so if I didn't have a 45 amp rated overcurrent device, you see that note 1, that would allow me to go up to the next standard size. But I know that in 240.6a, we do have a 45 amp rated overcurrent device as a standard device. So that's what we're going to do. So we're going to have a 45 amp primary if it was a 30 kVA transformer. You with me? Now, while we're doing it, somebody says to me, well, what if you chose to go to the 45 kVA transformer? Okay, I'm going to give you that since we're here. So I'm going to take the 45,000, do the same thing. I'm going to divide that by 831, and that is 54.15. I'm getting rid of that 0.15, and I'm working on 54 amps. Taking that 54 amps times 1.25, that is 67.5. Now, if I now go to 240.6 and I look, 240.6a that is, and I'll look and I'll notice I don't have anything at 67.5, but I do have a 70. And because I'm dealing with note 1, which says where the 125% of the current does not correspond to a standard size, then I can go up to the next higher standard size. So I'm going to put a 70. So I'm going to have a 70 amp. If it's a 45 kVA transformer, I have a maximum 70 amp on the primary. If it's a 30 kVA, I want to have a 45 amps on the primary. Okay? So again, depending on which transformer you go with, do you want the one that can just handle the load, or do you want the one that has extra capacity? It's totally up to you. It's your design. Again, price is going to dictate a lot of that, I'm sure. Okay. So that's what I've got. So that's my primary protection. Okay. Now, as far as the conductors, now, since I did those conductors and I went to that overcurrent, we still have to protect those conductors at their ampacity, right? So I'm going to be terminating those conductors into whether it's a 45 amp device or a 70 amp device, okay? So I have to be sure that I have a conductor that's going to terminate and be adequately protected by terminating into those devices. So I'm going to go to 31016 and I'm going to see if I can't find me a conductor. Now, both of these are under 100 amps, so you're probably thinking, Paul, you're going to be using the 60-degree column. I am not. One is because I'm going to say that the terminals are rated 75 degrees or greater, and I'm going to say that the conductor's insulation, which is modern insulation, is THHN, THWN-2, XHHW-2. All of those are going to be 75 degrees or higher. So I don't really have a problem with that. In 110.14 C1A, C1A, will tell me that as long as everything is rated, then it's fine. Okay, so I'm going to be using a 75-degree column. If you didn't know any different and you knew the lugs were 60 or you knew there was a weakest link, then you're going to stay in the 60-degree column. But here, everything's rated 75, so we're going to use 75. And this is not an exams question, so this is a real world. So I'm assuming you'll go check that out and you'll know what you're doing and you'll adjust yourself accordingly. Okay, for 45 amps, it looks like I'm going to need an 8-gauge copper. And if I'm running a 70 amp one, I would need a 4-gauge copper. Okay, so again, select your poison accordingly. But they would be perfectly fine, and they would be considered protected by the overcurrent protected devices. Now, again, I'm going to warn you, you're running 360 feet, so I don't want you to discount voltage drop. Even though the code doesn't mandate voltage drop, it's a recommendation. But, I mean, there's only 2 places in the code that voltage drop is a demand, is required. Sensitive electronic equipment, and dealing with emergency systems, right? Other than that, anywhere else, then it's not something you have to. It's optional to take into consideration, but it's important. I would most certainly would take it into consideration, right? Okay, but at any rate, so once we size the conductor, so I would choose either. Again, like I said, it would either be an 8 or it would be a 4, based on that. So this is primary. Primary is done. Okay. And then just, again, being aware of the distance. Now, when it comes to the secondary side, it sounds to me like all of your conductors are outside. So from that secondary, you don't need any overcurrent protection at that secondary. And all of that's going to fall under 240.21c. So that's transformer secondary conductors, which people refer to in many cases as taps, but they're not. They're really secondary conductors. But I think we all get to the same place we need to be when we're discussing it. So in this case, it's all outdoors. So it seems to me that you're going to be following the rules in 240.21c4, which is everything is outside. Now, the beautiful thing about this is you're not limited in those secondary conductors' length because it's outside. Now, you have conditions you have to meet and how it's terminated and what have you. But you don't have a length. It's not like the 10-foot secondary conductor rule or the 25-foot secondary conductor rule because you're outside for all of this, okay? So let's kind of look at that. So here's what it says for 240.21c4. For those that are following along, pause this podcast, grab your code book, blow the dust off of it. And it says, outside secondary conductors where the conductors are located outside of a building or structure, except at the point where they terminate, or the load terminates, which yours sounds like everything's outside, so it doesn't matter. And it complies with all of the following. Okay, so you have some conditions here, 4 conditions. Number 1, the conductors are protected from physical damage in an approved manner. Again, approved manner being whatever the AHJ is okay with. One of your other questions that you asked me was, should you run rigid? Up there, I think you said, should you run conduit or rigid is one of your questions. And they're both a raceway. So rigid is a conduit. So you ask it should be conduit or rigid. They're the same thing. But you have different types of conduits. You have intermediate conduit, you have rigid conduit, and then of course you have EMT, which is a tubing. It's not a conduit at all, but all of those are raceways. So your choice of what you want to run. I never ran rigid when I didn't need to. It's just too much to deal with, the threading and all that kind of garbage. If you ran EMT, just make sure you use compression fittings because sounds like in a wet location, all those type of things. Other thing I'll remind you, if you're running raceways on the roof, if you go higher than 7/8 of an inch, then you're going to have a rooftop adder, okay, which is something you have to follow in 310.15b2 in the 2020 edition, okay? So again, we're talking 2020 edition here. So anybody out there that says, wait a minute, that's not 2017, don't get your panties in a wad. I'm talking 2020 NEC, okay? So you also have to worry about your ambient temperatures other than the rooftop adder, right? Because of the location where it's the heat and the sun, and you still got an ambient that's different than the normal ampacities that we get in 31016, okay? So it's 30 degrees Celsius, 86 degrees Fahrenheit. If it's not that, then you're going to have to do some type of correction on that. And that's held in 310.15b1. And you're going to have to do something because it affects the ampacity of a conductor. Okay? So just things for you to think about in your installation because you are running across the rooftop. And you are going to have probably a difference in ambient temperature. Now, the adder might not come into play because you might not be installing higher than 7/8 of an inch above the surface, but you still have an ambient temperature you have to be aware of. So just keep those things in mind, and it is going to affect your ampacity. Okay, so that was the first thing. Okay, so protect in an approved manner, conduit, raceway, tubing, whatever you want. Approved means AHJ is okay with it and gives you the green light, go forward. The next one says the conductors, and these are those secondaries, terminate in a single circuit breaker or a single set of fuses that limit the load to the ampacity of the conductors. Okay? This single overcurrent device shall be permitted to supply any number of additional overcurrent devices on the load side. So remember what I said earlier about sizing your panel or sizing your transformer to maybe hit a panel with the main breaker? That's your single breaker. And then you could have other overcurrent devices in there. Maybe one of them that does handle the HVAC load, and then maybe another one that handles a receptacle that's within 25 feet. I'm just throwing that out there. But you also could come off those secondary terminals at the transformer and hit a disconnect for that HVAC unit, which is also a circuit breaker, which is also going to have the overcurrent protection and everything else that's required for that HVAC unit. And it's going to serve as the disconnecting means and all that wrapped in one. But one of the caveats is those conductors has to terminate into a single circuit breaker. So the question is whether it's fused or unfused that I think you ask later is irrelevant because it has to terminate into a circuit breaker or a single set of fuses. All of this has to limit the load to the ampacity of those conductors. Okay? Now, the other thing I will tell you is that the secondary conductors that come off of that transformer, you cannot use a next size up rule, right? And if you ever wondered where that is, right, you're looking at it, that is in 240.21, the body, and it's the last sentence. It says, conductors supplied under 240.21, 240.21a through h shall not supply another conductor except through an overcurrent protected device meeting the requirements of 240.4, right? So then you go on down and we're talking about other applications and say, okay, well, we're talking about secondary conductors. We have to jump over to C again. And if you look at C, what does that last sentence say? It says, and I'll read it, if I can find it where it starts here. Well, I might as well read the whole damn thing. It says a set of conductors feeding a single load or each set of conductors feeding separate loads shall be permitted to be connected to the transformer secondary without overcurrent protection at the secondary as specified in 240.21c1 through c6. Section 240.4b shall not be permitted for transformer secondary conductors. So what that means is if they don't correspond, you can't jump up to the next size. You with me? You get me? So whatever the load is here that we're going to be having, we have to make sure that our secondary conductors, one, can handle that load, but you're going to see in a minute that you're going to have another limiting factor when we're reading about the secondary conductors outside that are going to make those secondary conductors have to be at least sized based on whatever the overcurrent device is that you select in that HVAC disconnect. Okay? Sound like a lot? Sound like a mouthful? Don't worry, we'll break it down. All right, let's get back to our list here. So those secondary conductors, first thing that we automatically know, me and you, we know this. They obviously can't be less than the 78 amps because that's the load. But also, since our secondary transformer puts out a potential to handle 83 amps, so we already know it can't be less than the 83 amps, right? Okay. If we want to come. Now, I shouldn't say that. If the load is 78 amps, and we certainly can have the conductor's size to handle that 78 amps as long as that's what the load is, okay? Then we would be okay. The reason I say that is because you could have had this 45 kVA transformer with a capacity of 125, but I only needed to come off of that for this one HVAC unit, and it pulls 78 amps. So I don't have to size everything to the maximum capacity of that transformer. That's just what the transformer can supply. Doesn't mean that's what I'm pulling. You with me? Okay, so I got to make sure how I say that because I don't want to confuse anybody. All right, so now let's look at what we've got here. So in our case, let's kind of go through the pieces. So assuming we're going to terminate this into a single circuit breaker or a single set of fuses that limit that load, it says this single overcurrent device shall be permitted to supply any number of additional overcurrent devices. So like I said, you could feed a panel if you wanted. All right, number 3, it says the overcurrent device for the conductors is an integral part of the disconnecting means. Okay, so in this case, for the secondary, these conductors are terminating in the overcurrent device that is stipulated in number 2 we just read, and it has to be an integral part of that disconnect, or it can be located immediately adjacent or right beside it. So you could have the overcurrent in a separate, let's say, knife fuses, a knife switch, and right next to it, immediately adjacent, is the overcurrent devices, if you want it. Most people aren't going to do that. You're going to combine them all, okay, in order to do this. Either way, it sounds like we've got to have that. And then number 4 says the disconnecting means for the conductors is installed in a readily accessible location complying with one of the following. Okay, so we're talking about that disconnecting means now that is required for you to terminate those secondary conductors into, okay, which in our case is going to serve double duty, right? It's going to be also the disconnect for the HVAC unit. That's okay. But it says outside of the building or structure. Okay, we don't really need to go any further because it is all outside. Well, B, it says inside the nearest point of entrance of the conductors. Well, we're not penetrating, so that one doesn't apply. And C says we're installed in accordance with 230.6 nearest the point of entrance of the conductors. Now, that would be an example where 230.6 is talking about being outside of a building. So if we were like underground in a raceway and it came up, let's say, in the middle of the building, up into a service room, a switchgear room, or whatever room, then if it popped up into it, then it's got to come up, and nearest point where it comes in, it's got to come up and transition into this disconnecting means. You with me? Now, we meet this because it's just all outside the building, so we're good to go. So one of the things is we need a disconnect for the HVAC, but we also need this disconnect with this overcurrent protection that these secondary conductors terminate into. Okay, so I think that answers your other question for that as well. And I haven't read all the questions because I'm going to summarize them at the end and say what we covered and what we didn't. So there you go. Let's see. So that's taken care of. Now, let's talk about those secondary conductors here for a second, sizing those. So, but before we even do that, let's go on and work our way from the HVAC back now. Because remember what it says? Okay, from the disconnect down to the HVAC. Let's go on and work this out. It said that the minimum circuit ampacity was 78 amps and the maximum overcurrent protection was 100 amps. Okay, so more often than not, and you know this as well as I do, that when people are installing air conditioning units, they look at minimum circuit ampacity, maximum overcurrent protection. They always go to the max. They just always do. So you don't have to go to the max. That's the maximum overcurrent protection. But since the manufacturer gave you this, there's this probability maybe that it won't hold. I don't know. But we're gonna go with the premise this is what they give you. So in this case, it's 78 amps. So from that disconnect down to the actual HVAC unit. Now remember, we've already done everything all the way up to the transformer. And we're still working from the transformer out to the load, which is the HVAC. But we went on and jumped to the HVAC because remember I told you, treat this as normal, okay, when you're sizing this, okay? All right. So I want to go to 310/16 in this case here. And again, all terminals 75 degrees C, all insulated rated 75 degrees C or greater. I'm going to look for a conductor that's going to handle the 78 amps under 75 degrees C. So I'm going to go down, and it looks like it'd be a 4 gauge. So this 4 gauge is going to be able to handle, and again, copper. It looks like it's going to handle 85 amps. Okay, perfectly fine. So it's going to be a 4. So from my disconnect down to my HVAC unit, okay, then it's going to be a 4 gauge. Okay. Now, the next thing we're going to say is, okay, well, the maximum overcurrent protection is 100 amperes. So that's the size or the rating of the breaker that's going to be in our disconnect, which is also going to provide our overcurrent protection for this HVAC unit. Okay. Okay, so we've got that protection, everything there. So it looks like right now we have a 100 amp disconnect. We have 4 gauge copper from that down to the unit. We're good. Now, kicking it back to our secondary conductor sizing for those secondaries. Even though we know what this transformer's output can be, we still saw that we're now focusing on, one, making sure we have a conductor, one, it can handle all these loads, and two, we have to follow the rules to not have to have this protection of these secondary conductors at their from the transformer connections, okay? So we're going to go back again and look at 240.21c4, and more specifically, we're going to be looking at item number 2. And again, it says the conductor terminates into a single circuit breaker, so we're going to say it does. It comes off the secondary, goes right into the line side of this disconnect, okay? And it says it shall limit the load to the ampacity of the conductors. Okay, well, right now, that's a 100 amp rated device. And those conductors are rated for 85 amps, a number 4, right? So remember, they're on the line side, okay, of the protection for the HVAC, okay, the disconnect, which is 100 amp rated, okay? So that would not be meeting this rule because I can't do the next size up. I can't round up. So what I'm going to have to do is I'm going to jump up in size from that 4 gauge up to a 3. So from the transformer up to the actual disconnect for this HVAC unit, I'm going to increase the size to a 3 gauge copper because that's good for 100 amps. So that's going to meet the item number 2, which tells me since I had to have 100 amp for HVAC, and then it reminds me that it has to limit the load onto those secondary conductors, and it can't be less than the device that's going to limit that load. And since it's rated 100 amps, then my conductor is not going to work because I can't use that next size up rule for my conductors. So that means I'm going to have to jump from the 4 up to the 3, which is good for 100 amps. So I'm going to run 3 gauge from the secondary up to the disconnect, and then from the disconnect down to the HVAC, I can then drop back down to 4. Okay. Now, some people ask, I don't want to buy all these sizes. Can I just buy 3 gauge and run 3 gauge from the secondary to the disconnect and from the disconnect down to the HVAC? Absolutely. You can most certainly go larger if you wish. I don't have any problem with that. Again, making sure that your terminals can handle the increase in size, that type of thing. Okay. Now, since you're only jumping one conductor size as a choice, then I would not think your equipment grounds would need to change, the ratio deal in 250-122B because you're only jumping one size. But again, I have other episodes that talk about sizing and all that, but I wouldn't think that would be your condition that you're running into. But again, you do you, and you got to check it. But at the end of the day, that's what I would say is your sizing. Okay, so hopefully that helps that out. So I'm looking at all your questions here, and let's see if we can kind of recap. So number one, what is the overcurrent protective? Oops, hold on, I dropped it. What is the overcurrent protective device rating for a 480 volt main? And I think I gave you that. It looks to me like it would be a 45 or a 70, depending on whether you're doing a 30 kVA or a 45 kVA, your choice. Whether you want that additional capacity, whether you're installing a panel with maybe trying to get other loads out of it, like for that receptacle within 25 feet or whatever. So you've got that option. So in the conductor sizing that we did on the primary side, so what we're running up to that, I think we sized that out and we were good to go. I think that was an 8 gauge or a 4 gauge. I think we covered that. Let's see, for primary side. And then, of course, we have the transformer, and then we talked about the secondary conductors. Since they're all outside, we use the 240.21, and we use the outside rule, which is secondary, which is C4. We terminated into a disconnecting means, and then we paused for a second and made sure that we sized that disconnect and everything to the HVAC to cover its rules in 440. We basically used the nameplate because that's what we were given. And then once we established what that disconnecting was in the secondary, then we could size those secondary conductors to make sure that they complied to this rule in 240.21C4 so that we didn't need protection for those secondary conductors at the transformer. Okay? And the only other thing I'll remind you in all this is be aware of that 330 feet. That is quite long. One of your other questions here was, what size of primary disconnect, fused or non-fused? I think I kind of covered that already when I discussed the rules here. For that, either if it's a 45 kVA, it'd be a 70. If it's a 30 kVA, it'd be a 45. That type of thing. So I think I've already covered that one. Says, do I need a disconnect at the HVAC unit, fused or non-fused? I think you'll find that you most certainly need the disconnect because the rules tell you that you have to have a disconnecting means in Article 440. But in your case, because of your secondary conductors and because you're wanting to use this secondary conductor rule, you're going to have to terminate into them anyway, a circuit breaker. And of course, you still need your protection, right, for your HVAC, and you follow the nameplate, maximum minimum circuit ampacity, maximum overcurrent protection. So it just takes care of itself. So I think that covers you. So maybe that answers all your questions, whether you're using a 30 kVA or a 45 kVA transformer. That kind of same concept either way. And hopefully that'll help you get through that question. All right. So anyway, kind of a long one today. Hopefully that broke it down so that you have kind of a basic understanding of real world applications. I would not, again, have any problem with installing a 30 kVA transformer for this application, knowing I'm going to get 83 amps out of it. Again, some engineers will say, no, I need more capacity. I need to have a buffer. And I know plenty, and I'm just telling you just from experience, who will look at the next available size transformer and bump you to it and say, okay, well, I'm going to bump you. I want you to go to a 45. And you're going to get some extra capacity out of it. And maybe you're going to do it like I told you. Maybe you're going to install a panel, a NEMA 3R panel, and that way you have the ability to get other loads out of it. So maybe you're going to do a 480 to a 208 120, and you're going to be able to use that in order to be able to get that receptacle that you need within 25 feet. I don't know. Just kind of throwing a lot of stuff out there at you, hoping that it'll help you out. Okay. All right. Well, that's it, folks. If you got any additional questions on anything, you know what you can do. You can simply go to Let's Ask Paul over at the paulabernathy.com portal. Submit your question. If you agree with this podcast, great. If you disagree, oh well. I eagerly await your podcast and your opinion on how you would address these issues. But based on the conditions that are given, based on the limited data that we know, that's what I got for you. Till next time, folks, stay safe. God bless.